The next flip-flop that we are interested in is the JK flip-flop. It's also known as the Jack Kilby flip-flop. So Jack Kilby was the first engineer who designed the integrated circuit. So the first integrated circuit was designed in the year 1958 by Fairchild Semiconductor. And Jack Kilby was the engineer who was a part of a team who designed that. He got a Nobel Prize in the year 2002, I believe, and he died in the year 2005. He was born in the city of, I think it was Jefferson City, Missouri. So let's see what Jack Kilby did. First, the symbol for the JK flip-flop is input J, input K, Q, Q prime, and input clock. Let's see how this works. So input J, input K, Q, and Q plus. So let's take the 8 combinations. When J and K are 0, 0 and Q is 0, your Q plus will be 0. And when JK are 0, 0 and Q is 1, it's going to be 1. So that's the hold operation. It's similar to the SR flip-flop or the SR latch. Again, now when J is 0 and K is 1 and Q is 0, your output will be, or your next state will be 0. And even in the second case, it's going to be a 0. And this corresponds to the reset operation of the SR flip-flop or the SR latch. As you might have guessed, the next states for J equals to 1, K equals to 0 would be 1, 1. So that's the set operation of the SR flip-flop or the SR latch. And finally, when J equals to 1 and K equals to 1 and Q is 0, your output is going to be a 1. And for the other case, your output is going to be a 0. And this is known as the toggle operation. So it's very much similar to the SR latch, with the only difference that in your SR latch, you're not allowed to have the inputs 1 and 1. But in the JK flip-flop, you're allowed to have the inputs 1 and 1. And when it is 1 and 1, your output is going to toggle, which means if your previous state was 0, your next state would be a 1. And if your previous state was a 1, your next state would be a 0. So let's take two examples to understand how this works more clearly. So here you're asked to complete the timing diagram for the rising edge triggered JK flip-flop. And we are going to assume that Q starts at 0. So let's mark all the rising edges 1, 2, 3, 4, 5, and 6. Now at the first rising edge, J is 0, K is 0. So that's the hold operation. So continue to hold the value. At the next rising edge, J is 1 and K is 1. So that's the toggle operation. And when you have toggle, after a slight delay, your Q was 0 before, so now it's going to be a 1. At the next rising edge, J and K do not change. That is, they are 1 and 1. So again, we toggle it. So after a slight delay, Q goes from 1 to 0. At the next rising edge, J is 0, K is 1. So that's the reset operation. And since it is at 0, we are still going to remain at 0. At the next rising edge, J is 1 and K is 0. So that's the set operation. Therefore, after a slight delay, it's going to set to 1. And finally, at the next rising edge, J is 0, K is 0. That's the hold operation. So we continue to hold the value of Q. Let's take one more example. So here, you're asked to complete the timing diagram for the falling edge triggered JK flip-flop. And we are going to assume Q is at 0 initially. So mark all the falling edges. So 5. Initially, the value of Q is 0. So it's going to remain 0 until the next clock cycle or the falling edge cycle. So at this falling edge, J is 1 and K is 1. So that's the toggle operation. Therefore, after a slight delay, it's going to go to 1. At the next falling edge, J is 0, K is 0. That's the hold operation. So continue to hold the value. At the next falling edge, J is 0, K is 1. That's the reset operation. So Q goes to 0 after a slight delay. At the next falling edge, J is 1 and K is 1. That's the toggle operation. Therefore, after a slight delay, Q goes to 1. And finally, at the next falling edge, J is 1 and K is 0. That's the set operation. Since it is at 1, since it is already at 1, it's going to remain at 1. So that is how a JK flip-flop works.